Hello everyone. It's been a while since I did a math video, but I recently watched a video on YouTube that sparked my interest about a specific aspect. Now, ironically, the video had nothing to do with math specifically, so there's no point in me referencing it directly. It just sparked the thought. See, for some time I've been wanting to talk about how numbers are really just loops disguised as digits. But it's such a large topic to get into. I haven't really fully found all the thoughts that I want to express on it. I haven't collated them. But there is one area that I can speak into. It deals with a simple observation. When you divide 1 by 9, the result is a repeating decimal, specifically 0.1111 and so on. Now, I had first learned this back in elementary school probably, almost certainly, but a few years back, I was playing around with base 6 mathematics, and I found something odd while just messing around. In base 6 math, 1 divided by 5 is, you guessed it, 0.1111, and so on. In fact, pick any base other than binary, and you're going to find the same result. Whatever base you're in, 1 divided by a number that is 1 less than the base always results in that repeating decimal of 0.1111 and so on. Now I mentioned that this is aside from binary, and that's because it's base 2, and 1 less than 2 is 1, and 1 divided by 1 is 1. So there's no repeated decimal there, but let's just look at the other bases. The first thing to remember with bases is that the digits in a base follow a very simple rule. If we think of a number like 231, we can write that out as 2 times 10 to the second plus 3 times 10 to the first power plus 1 times 10 to the 0 power. But what if somebody comes up and says, no, you were mistaken. This isn't 231. This is actually a number in base 8. Now, how do you calculate that? Well, it's actually really simple. Instead of the times 10 to the whatever power, you replace that 10 with 8 because that's the base we're in. We're in base 8 now. So instead, we would have 2 times 8 to the second plus 3 times 8 to the first plus 1 times 8 to the 0 power. So given that this is how digits are represented, we can come up with a specific rule or pattern for this process. So let's define a number n as a series of digits d in base b, where b is a positive integer greater than or equal to 3, as follows. N equals d sub 0 times b to the 0 power plus d sub 1 times b to the first power plus d sub 2 times b squared plus d sub m minus 1 times b to the m minus 1 power plus d sub m times b to the m power. So in this example, 183 and base 10 would actually have the following values. D sub 2 equals 1, d sub 1 equals 8, and d sub 0 equals 3. Our b for base is 10. So therefore, in this structure, we would say 183 equals 1 times 10 to the second plus 8 times 10 to the first plus 3 times 10 to the 0. Decimals are represented in the same way, except instead of positive exponents, we're dealing with negative exponents. So for example, still in base 10, what would 42.7 be? Well, that would again start with the 4 times 10 to the first plus 2 times 10 to the 0, and then you would say plus 7 times 10 to the negative 1, the negative first value. So given this, we can now represent the values of what we're going to be looking at. N equals 1 over the quantity b minus 1, where b again represents a base that is an integer of 3 or greater. My claim again is that in any base b, then 1 divided by the value of that base minus 1 is going to result in a repeating decimal of 0.11111. And my claim is this is true for any base greater than or equal to 3, right? That's what this represents. So how do we solve this? Well, I mean, we just do it, right? We divide 1 by b minus 1. But what does that actually mean? When you're just looking at it, there's no way to really reduce this fraction. So How do you solve it to get an actual value out of this? How do you get to that 0.111 that I'm claiming is there? Well, let's get back to the basics. What exactly is division? So the actual question is, how many times does b minus 1 go into 1? That is what is meant by the process that we're doing. Now, before we dig into that specifically, let's just ask a simple question so we're all on the same page together. Suppose I ask you how many times does 2 go into 4? Now, almost every one of you can just do this in your head, but my point is to give us a procedure to do this. Pretend you don't know how to solve it. Pretend you don't already have that memorized. What is the process by which you would solve this from scratch? So the very first thing you do is you ask, is 2 bigger than 4? Obviously not. No, 4 is a larger number. So that means that 2 can go into 4 at least one time. So we can write that 1 over here, and that means that we can now subtract 2 from 4 and see what our remainder is. Well, 4 minus 2 is 2 again. And so the question is 2 bigger than 2? And no, it's not bigger. It is the same value, so it's not bigger. So that means we can take another 2 out. And when we do that, the number at top becomes 2, because we've taken out 2 1s, and we subtract 2 again, and 2 minus 2 is 0. Now we can't go further than 0, so we've gotten our answer. We can take 2 out of 4 exactly 2 times, and there's no remainder left over, so we're done. But what about if we divided 10 by 4? Again, we see that 4 is less than 10, so at least one 4 gets pulled out. 10 minus 4 gives us 6. 6 is still bigger than 4, so we just pull out another 4. This gives us 2 times where we pulled out a 4, and then we left with 6 minus 4, which is 2. Now what do? 4 is bigger than 2, so we can't pull another 4 out of 2. At this point in elementary school, you might stop and say, well, the answer is 2 remainder 2. But we can go further here. Sure, 4 isn't bigger than 2, but you know what is bigger than 4? 20 is bigger than 4. Now, I know what you're thinking. Wait, how did you get 20 from that? We know you just write the point and you drop the 0 down, and then you're looking at 20 instead of 2. But what is actually going on? What justifies this? So in reality, what we're doing isn't saying 4 is greater than 20. We're actually literally saying 0.4 is smaller than 2. Now, 0.4 is smaller than 2 is the same equivalent thing as saying 4 is smaller than 20. That's the same thing, but we're shifting bases while we're doing it, and it's kind of hidden behind the scenes. People don't really explain this very well, but if you remember our decimal notation from before, 0.4 is the same as 4 times 10 to the negative first power. So because 4 is too big to take out of 2, we instead look at the fraction of 4 that can be taken out of 2. 10 is the base. We're using the negative 1 as the first shift over. So that means that if we were doing this division in, say, base 7, then we'd say since 4 is bigger than 2, we'd really be looking at 4 times 7 to the negative first power into 2. The base we are in stays consistent throughout, and then the math just works. So with that in mind, let me again look at our original equation. N equals 1 over the quantity b minus 1. Since b is 3 or greater, then we know that b minus 1 must be greater than 1. So let's write that in. So we're starting. Given n equals 1 over b minus 1, and b is a positive integer greater than 3. Greater than or equal to 3. Let me be clear on that. So clearly, the smallest b that can be there is 3. And 3 minus 1 is 2. 2 is bigger than 1. So no matter what number we use for b, b minus 1 is necessarily greater than 1. Right, so we've got that fact in place. Now what does that tell us? If b minus 1 is greater than 1, then 1 over b minus 1 must result in an answer less than 1. See, if b minus 1 is greater than 1, then the denominator of the fraction is bigger than the 1 that's on the numerator. And since 1 is always the numerator, this means that the denominator is always bigger. So as a result, 1 divided by b minus 1 will always give an answer smaller than 1. So as a consequence of this, when we begin our decimal expansion, the result will have to begin with a 0 point and then something. So what do we do to solve this? So remember, when we have a smaller number being divided by a bigger number, then we have to get to the next base down. So what are those bases here? Well, first we need to remember this. So b to the 0 power is 1. This is true because all bases to the 0 power are 1. That's part of the definition of what an exponent is. And secondly, we know b to the first power is b. Again, this is true because all bases to the first power are simply that base. So again, this is the definition of exponents. Hopefully it's not too controversial. Given this fact, we can rewrite our original equation as follows. N equals b to the 0 power over the quantity b to the first minus b to the 0. This is done by substitution from the previous steps. Now, what's next? Well, since we just showed that b to the first minus b to the 0 is greater than b to the 0, which is just another way of saying b minus 1 is greater than 1. This means the fraction we just created for step 5 is also shown to be less than 1. So again, it will start with 0 point something. Since the fraction we have in step 5 is less than 1, we have two options to continue. Now these are the same steps from division we already looked at previously with integers. We need to see what fraction of b to the first minus b to the 0 power actually goes into b to the 0 power. And we can evaluate that next step by either looking at how much b to the first minus b to the 0 goes into b to the first power, or we can look at how much b to the 0 minus b to the negative first power goes into b to the 0 power. These are equivalent notions, so it doesn't really matter which one we take. It's roughly the same as the difference between 0.4 to 2 as it is from 4 to 20. That's the only difference between these two notations. And remember, we started with the fact that b to the first minus b to the 0 power is greater than b to the 0 power. So we have to start off with 0 point something here. Now after that, we'll take the first branch and ask, how many times does b to the first power minus b to the 0 power go into b to the first power? And we can see that b to the first minus b to the 0 power is less than b to the first. So that means b to the first power minus b to the 0 power goes into b to the first power at least one time. So we will write down the 1 next. And remember, the next step is that we then subtract b to the first minus b to the 0 power from b to the first power and see what we get for the remainder. And that's very straightforward to solve. If we start with b to the first power and then we subtract b to the 0 less than b to the first power from that, we are left with b to the 0 power. But wait, b to the 0 power, that's what we started with. That means that the process will simply repeat itself every time we go through this, each time adding another 1 to the decimal expansion. In other words, we've just proven that for all bases greater than or equal to 3, 1 over base minus 1 equals 0.111111 forever in the decimal expansion. Pretty neat, huh? And with that, I hope you all do have a wonderful day.